I would like to invite Vidhee AVASHIA from IIM Ahmedabad. I'd like to hand over the mic to you.
Thank you. So, thanks so much for this opportunity. And moving from the heat, we talk about the other impact now, precipitation. So what we've done here is looked at how land use change impacts localized flooding in cities, because the urban land use is a very different characteristic than the rural land use as such. So we've tried to do this for 42 Indian cities. To give you a background in the context, by urban India, it's urbanizing, and we're expecting almost 50% of the population to live in cities in India by 2050, and that means almost above 700 million. There are 9 big cities already with 5 million plus people, 52 cities between 1 and 5 million population. And across time, when governments and other agencies have tried to audit situations, they have found that cities suffer from lack of basic services. The biggest one of them being the drain and the storm supply systems. Governments have tried to improve it, but still there is much more need. And given the climate change impacts that cities face, we do expect that as the temperatures change and the precipitation patterns change, the cities might experience a lot more of localized flooding. We already see that happening at some places. So if I'm here using a schematic of the city that I live in, Ahmedabad here. So currently the city land use looks like this. So whatever is yellow is constructed space. But in future, it would look like this. And this is what the master plan of the city has come up with for 2030, 35. So as the city grows spatially, and the temperature and precipitation situations change under various scenarios in climate change, we do expect that a lot more of extreme rains would happen in these cities, and for these cities to absorb all that water would be an issue. Hence, a lot of national policy has also started giving a lot of importance to what's happening with cities in India. There's a national mission on sustainable habitat in India, and each state in India is supposed to create a state action plan on climate change where they look at what will happen in their state and all. But still, urban land use has not become a prominent indicator yet. That's why we started with the urban land use. Again, when we look at the climate projections in India, we do see that already a large number of districts are falling into what would turn out to be 4.5 or 8.5 RCP related impacts on precipitation. Moving forward, hence we frame this research question where we try to see what are the implications of urban flooding within the current extreme event situation, and what would happen in future if the land uses change. For this, we started with understanding what kind of cities we want to look at. So we looked at 3 different categories of cities across various climate zones. So we picked up 42 which fall under different climate zones. So these are the climate zones that you see, and these are the city sizes. So Z size is the smallest one, which is below 1 million. Then Y and X is the above 5 million sort of cities. So this is the list of the cities. What we here did was look at data on past flooding events. So we collected this flooding events data, we collected land use data, so we processed satellite images here. We got historical rainfall data, and then we put it into a multi-level regression model. And we also used the future climate change projections as well as future urban development scenarios to see what would happen in future if similar land use growth happens to across these cities, etc. So to give you an idea of how we went about looking at the satellite images, so we processed that, we got the land use breakup, we took the Landsat images across these cities for 4 different points in time: 1990, 91, 2000, 2010, and 2017 to 2020. This is a 30 meter by 30 meter pixel area. So to give you an example of what Bangalore would look like, is we have 65,000 pixels for Bangalore city alone within its city boundaries, right? We took the hybrid classification approach and classified the land uses into agriculture, urban built-up, green spaces, open spaces, water bodies, and then certain cities, because of their characteristics, there were beaches, rivers, sea, swamp, snow that we found. We did hybrid classification, validated the Google Earth and GIS online for Landsat, and reached accuracies within these classification processes anywhere between 79 to 93% across cities, across 4 timelines. So that's something that we believe is good enough to move forward. So this is the output that we got when we did the classification. So again, using Ahmedabad as an example, I'll show. So this is what the city looked like in 1990. All the red spaces are constructed spaces, and the yellow ones are agricultural lands, right? In 2000, the spaces had increased, and when you see the 2010 map, you could see it's almost everything's red, everything's constructed. There's not much of open green spaces left or water bodies left within the city. So to give you an idea, further zoomed in, this is how all red the city has become beyond 2010 as well. Next, we looked at flood events data. So for this, we had to do an event count study. We went into the Times of India archives. Times of India is one of the oldest running English newspaper in India, which covers across the country various editions. We looked from 1991 to 2015. And then based on all the event counts, each news article that we could skim through, we've created a database of what floods happened where across these 42 cities. And we found there were almost 1,246 data points that we could use. For the rainfall data, we used the gridded data available from Indian Meteorological Department. And this was, again, inverse distance weight interpolated to 0.25 degree by 0.25 degree resolution. So it was good enough for us to understand what is the historic rainfall to match with the historic flooding that we had from the articles, news articles. This we put into a multi-level model. So we decided not to take up a simple regression model here, because we do see that if you look at this, we do see that the city has a relationship with the rainfall. The rainfall influences flooding, but then there is also city level characteristics that influence the flooding. So in order to ensure that this latent relationship is captured in the entire process, we decided to use a multi-level model where we use the city as a cluster, as a level. So the initial level 1 equation is what we've displayed here. Then within that, we have the level 2 equation, which talks about land use change in the city. So this was our final combined equation that we used. We did all the analysis in R. Moving forward, the results. So we do find that as the non-built up land use, which is all the spawn spaces like open spaces, green spaces, blue spaces, and agricultural lands, when that had a negative relation. So as the green spaces decreased, the flooding events increased. we did this, then try to project it for future. So we used RCP 2.6, 4.5, and 8.5. Future rainfall precipitation numbers and 3 different scenarios for the urban growth. So business as usual scenario, or tiered growth, where we mapped the smaller cities with the bigger cities saying their growth rate will be. Oh, sorry, just this is the last line. Thanks. So and then we did a sustainable development scenario where we said the green spaces have increased and have gone to the shares where it was in 1970s. And we do find a lot of difference here when we try to see how many flooding days change. So this is the historic number across scenarios in future. If urban development happens the way it is happening, there's a lot of flooding to be expected. But if the green spaces increase in future, we are resilient. We would be resilient or adaptive enough to take care of the flooding events. So that, again, I not want to repeat in the interest of time. So thank you, everyone. Any questions?
Yeah, any questions? Thank you very much, Vidhee. Thank you. So any questions from the floor? You can type it in the chat box or just raise your hand for asking it. Okay, I have found the first question. Okay, it's from Gajiva Vandel List, and thanks a lot for the interesting presentation. Could this be generalized to other cities, countries, world regions? How about it, Vidhee?
Yes, of course, because we are considering city-specific characteristics. So if you have the satellite data, this model is very much usable wherever you want.
Okay, so
yes, the data, the way we have collected data is available everywhere. It's NASA free data set. So, yeah.
Okay, and any others? Any other question or comment? Yes, we have 2 more, and yes, the earlier one is from Francesco. There is not much difference across RCPs. Was that expected? Does that depend on the period chosen? That's the question from him.
No, actually, we didn't expect so much of similarity between RCPs. So when we tried to do the t-test between RCP 2.6 and 4.5 and 8.5, we found that, yes, 2.6 was significantly different, but across specifically the BAU and the tiered growth scenarios where the urban development happens and the construction happens quickly, we didn't expect that 8.5 and 4.5 will be so very similar. It basically, the first reaction was, oh my God, we're doomed. Our cities are going to flood and we need to do something about it. That was our reaction because we didn't expect it to be so similar. Yeah. Okay,
thank you for the answer. And we have, maybe 1 more minute and we can take 1 more. It's from Bredrag. And do you assume that there is a difference in the mean city level temperature depending on the development strategy? For example, urban greening policies. In other words, is the urban heat island accounted for? That's the question from Bredrag.
Yeah, thank you. We looked at precipitation, not the heat island as such. Yeah, we just saw what were the expected rainfall that might happen in the future or what's happening right now.
Okay. Thank you. So thank you very much. Yes, Vidhee. So we are almost running out of time. So thank you very much for your good presentation. And now I would like to invite the 3rd speaker, Mr. Francesco BOSELLO from CMCC.
Okay, so good afternoon, good morning, everyone. Thank you for the opportunity to present this short overview of our research. this is what I'm going to present stems from are the results, part of the result of Horizon 2020 project, the coach project that just ended and involved 13 partners, 13 research institutions across the EU. The aim of the project is to improve the knowledge of climate change impacts globally, but with also a specific focus on the EU. One characteristic of this research and novelty is to improve the resolution with which we present also the macroeconomic implication of climate change impacts. The other is to investigate also those that we call the social economic tipping points, so situation where huge economic losses could be experienced at a more local level without the necessity to invoke catastrophic events. However, my presentation today will focus on the macroeconomic effects, not on the tipping point part of the research. The methodology is highly multidisciplinary, so let me just mention the fact that the macroeconomic results that I'm going to show, which are based on the use of macroeconomic models or one specific economic model, are just the end of pipe result of a huge research that before specified climate scenarios, climate change impacts, then provided the information for the economic assessment. And furthermore, there is a further step that we are not going to touch today, which is also the policy implication of these macroeconomic impacts. The model that we are using for the assessment is general equilibrium model, computable general equilibrium model. Here you see the sectoral and the regional disaggregation of the model. Just let me mention that for the EU, we were able to develop a sub-national description of economic systems. So the European Union is represented by 138 smaller administrative units. So the space or the environment for our impact assessment is represented by this picture. So it is a mix or combination of RCPs, representative concentration pathways, and social economic scenarios, where you see the X is the combination that we are taking into account in the exercise. In addition, within each of these combinations, we try to take into account at the maximum level possible the uncertainty to give a comprehensive overview of the uncertainty space. So we did take into account the variability within scenarios that climate models and impact model were able to represent. So we have high, medium, and low impact cases within each of these combinations. And we also developed some sensitivity analysis on the social economic adjustment, specifically focusing on international capital or investment mobility, which we found is one of the most important drivers of macroeconomic results. So to summarize all this research in one picture, I'm going to present here what are the impacts of climate change for the EU regions in 2070, putting together all the results from the impact, socioeconomic and climate change combination. So you here see this cloud of results referring to each of the 138 European regions, all pulled together, and just on average, or to be more correct, on the median case, shows that impacts are 2.2% of regional domestic products, which is quite higher compared to the previous estimates produced in similar studies. What is also interesting to note is that there is a non-negligible number of European regions where the loss is higher than this 2.2%, which is higher than 5%. This is also particularly concerning and or interesting, and taking into account that this analysis just accounts for a subset of the potential impacts of climate change, those that are more suitable for economic market evaluation. So we do not have health cost and ecosystem biodiversity loss in this assessment. So to give you some quick insights on the relevance of the scenarios, let me drive through this picture. So first of all, we identified some smoothing mechanism, so something that is able to reduce somehow the impacts. And one of these smoothing mechanisms is the existence of international trade. And if we focus on this picture where the SSP3 scenario is developed, where this, the SSP3 is a scenario that we implemented with trade restriction, we can see that the impacts or negative impacts on GDP tends to be higher. So having more trade is a smoothing factor for impact. At the same time, and this is the right picture, international capital movement, on the other hand, is an amplifier of negative impact. And you see that the impacts are higher on the upper, in the upper part of the picture, where we have high capital movement across region, because we found that these capital movement tend to export somehow negative impacts. So we have these two mechanisms, that one smooths and the other amplifies the effect. And we can also see that more or less we have some kind of confirmation of the north-south, that in our case is more north-west southeast divisions of the impact. So the southeastern part is more damaged than the northwestern, even though the picture is a little bit mixed. Just to give an idea on what are the uncertainty sources for, or what drives the variability on our results. And we can see here that the major source of uncertainty does not come from the choice of the climate or the social economic scenarios, so the RCPs and the SSPs, but is mostly driven by the intra-scenario uncertainty, so the, let's say, variability of climate models or the impacts models that within the same climate scenarios. So this is important to highlight, but also on the macroeconomic or the economic adjustment that we take into account. So this is an important point to take into account for also next research. Here, finally, and I'm coming to the conclusion, some impacts decomposition, because we may want to know what are the major sources of impacts in the study. Here we have all the categories or impact areas that we take into account, and we see that the two most important drivers of impacts, or of macroeconomic impacts, of course, are related to those impacts that affect the capital stock. So sea level rise first and river floods second, even though depending on the scenario and the case, also impacts on energy demand or impacts on labor productivity can be very important. And here you see also the national, let's say, distribution of these impacts. And you can also notice that sometimes agricultural climate change impacts on agriculture in the EU could induce some positive effects or gains in terms of GDP. So let's come into the conclusion. This is the comparison of our results. You see all the red dots. So this is a sort of reduced form picture of our results, where we put in relation temperature increases on the x-axis with the loss. The red dots are those coming from our study, and the green dots are
Thank you.
Yes, thank you. And the green dots are those from the existing literature. So we can see that we have found higher estimates. This is the global picture than the previous literature. This also emphasizes that there are important potential inertias, because you see that impacts can be very high even though the temperature increase is below the 2 degrees Celsius. And these are the conclusions. The two most important points, I think, are that mitigation and adaptation are very important, because on the one hand, mitigation should help us to stay below the 2 degrees, but we have seen that also in these scenarios with the low temperature increase, there are a lot of potential impacts and high losses, which implies that we need to use adaptation. That's it. Thank you very much.
Thank you very much, Francesco. And as you have found in the chat box, by my mistake, I have invited Francesco first, and I've skipped Victhalia. So next speaker will be Victhalia. But anyway, we have, 3 or 4 minutes for QA. And if you have any questions to Francesco, please write it in the chat box.
Yeah, thanks for the presentation. One thing I just didn't catch at the end, you showed the comparison to the toll review study,
yes.
and it was labeled as world. So those are global impacts from
Yes.
your results?
Yes, I just take a summary, because we have results for the EU, for each single EU country, for each single EU region, and also for the aggregates. So I just choose the aggregate, which is more summarizing. Yes.
The aggregate for the EU, or
no? The last one was the world.
Okay. So because those are substantially higher than your EU aggregate, right? Which you said was about 2%.
Yes.
So I'm interested if some of your conclusions about uncertainties and main drivers of the outcomes are similar for the world or different?
Yes, they are. Yes, they are similar, even though with our research, so we noticed that both the global and the EU estimates were higher with our study, but the increase is higher for the EU. So we didn't. So the really new result is for the EU in our case. The source of uncertainty is exactly the same. The source of uncertainty is exactly the same. It's also true that for the EU, we had much more data to compare and to use to develop this uncertainty analysis. So this can bias a little bit the results, because we have 138 regions for 9 combination of scenarios with 3 different combination of impacts with 2 different combination of economic adjustment. So a much ampler cloud of data to process.
Okay, thanks.
Thank you. And we have 1 more minute and 1 hand raised, and it's from David.
Hello, Francesco. Thank you for
David.
your presentation. This is David from the ERC.
Yes.
We at the ERC have identified that health-related impacts are one of the strongest drivers in the EU. Is it intentional that you leave this category outside of coach, or can you give us some ideas?
Yes. No, that I didn't explain myself well, also because for this, but health impacts are definitely inside the research of the coach project. they are not, we have not used them for the economic assessment. So we do not have priced them. So there is a deliverable of the coach project where health impacts are analyzed and everything is reported in terms of additional death, mortality, morbidity, but we are not using the economic assessment of health impacts inside the macroeconomic assessment.
Okay, they are not monetized. Okay.
Not monetized, yes.
All right.
And I can also reply rapidly to Yunya. Yes, the damage on infrastructure are impacting the growth of the economy because we assume that they destroy productive capital. And given that the economy is a dynamic, represented by a dynamic process, we have less capital, and that build up across time, period by period. So basically it is exactly a negative impact on growth.
Okay, and thank you very much for responding to the question. And now time is up. So thank you, Francesco, for the presentation.
You're
and
welcome.
Now, yeah, thank you. Finally, we would like to invite the fourth speaker, Vidhee, AVASHIA, Victhalia, ZAPATA, Castillo from Utrecht University. Thank you for waiting for your order.
Good. Thank you all for coming here. I'm Victhalia ZAPATA, PhD candidate at Utrecht University, and I'm presenting my research about climate change impacts on primary energy production, which is a model comparison. It is well known that our energy sector not only causes climate change, but is also impacted by it. And as we know, the larger the share of renewables in the energy mix, the increased in vulnerability. Previous research on this topic have concluded that there is still a need for integrated analysis of climate impacts, both across regional and global scale. And therefore, for our research, we are focusing on our objective is to evaluate the impacts of climate change on primary energy generation under different climate scenarios, and to analyze its uncertainty by conducting a model comparison between two integrated assessment models, IMAGE and GCAM, and for climate models, general circulation models, from the ECMIC-2B protocol. So the method for this research can be explained in two main parts. The first part is from climate to resource impacts, and the second one from resource impacts to energy system impacts. Our research builds upon the results from the first part, which is based on the work of Ahmedabad et al. 2000 of this year. For this first part, climate data and socioeconomic data, differentiating between historical and future projections, were implemented for obtaining technical and economical potential gridded maps for the main renewable technologies. Our focus is mainly on renewables, and these maps were available for 8 technologies. Then for the second part, we implemented these potential maps for making tailored cost supply curves for the IMAGE and GCAM and for the different scenarios. As a result, we obtained climate impacts on primary energy generation, which we were able to compare between the integrated assessment models and also across using data from 4 climate models. So the scenarios that we ran are the ones that you can see here. For the model comparison, we implemented 6 scenarios that were proposed, in which SSP2, which is the middle of the road scenario, was crossed with the RCP60 and with the RCP26. These 6 scenarios can be described in 3 sets. The first set is where the integrated models, IMAGE and GCAM, implement cost supply curves with historical climate data only for all renewables. The second set is We implemented the cost curves with climate impacts for all renewable and also for both scenarios, the baseline and the mitigation one. And for the last set, we did 2 sensitivity runs for analyzing climate impacts on a specific energy source, which were one set of run for biomass and another for wind. These 6 scenarios were run 4 times each for being able to compare between the different climate models. So for showing the results, I mainly here for this presentation will focus on the results of the integrated analysis and for the period 2071 to 2100. In this research, we analyze climate impacts on the system by analyzing the difference in primary energy production between the runs with and without climate impacts. In the horizontal axis, you have the 4 renewable sources, and also for fossil, the climate impacts were analyzed as indirect effect by system compensation from the changes in renewables. The blue cells indicate an increase in primary energy production by climate impacts, and the red cells indicate a decrease in so a negative impact by climate change. So here we can see the results for the 4 climate models. And first, we can see that for the system analysis, climate impacts are not direct, as they depend not only on the input data, but also on system compensation between the different sources. IMAGE and GCAM depict a similar impact on the use of different energy sources, ranging from -20% to 20%. Also, most of the combinations, region source combination have impacts below 10%. It's important to highlight that for the bioenergy impacts, the analysis was done considering the effect of CO2 fertilization on yields. And this CO2 effect, fertilization effect is positive on the yields, and then that's why we can see that for biomass and bioenergy, we have mainly positive impacts or an increase in primary energy production. For the world, and under this scenario, we can expect, as you can see, an increase in average renewables of 6%, mainly because of the increase from bioenergy. Now, I will show some robust findings. These robust findings across the models are based on results that I can see in at least, are consistent in at least 3 GCM runs, and also between IMAGE and GCAM, that the signal, whether positive or negative. We can see here an increased use in hydropower and wind energy for West Asia. This increase is consistent between IMAGE and GCAM. An increase in hydropower use for China as a consequence of larger surface water runoff, and a decreased solar energy use for India. Continuing with our next integrated scenario. Now, this scenario, which is the SSP2 mitigation scenario that leads to 2 degrees towards the end of the century, is characterized by, first, more renewables, which then can lead to an increase in climate vulnerability. And second, it has less climate change, and therefore less exposure. So here you can see the results for the 4 climate models. And it can be noticed that the results show more variation between the signal response, positive or negative, between GCAM and IMAGE. Reasons for variation between IMAGE and GCAM are different economical and technological assumptions, and also there's some differences in the modeling power investment decisions in calculating the levelized cost. In average, for the world, we can expect under this mitigation scenario a 5% increase in the use of renewables, which is slightly lower than the impact under the baseline scenario. Some robust findings across the models are lower impacts on bioenergy use, and even for some regions, you can see some negative impacts, especially for Pacific OECD regions. Also, you can expect an increase in hydropower use in West Asia, which is Asia excluding China and India, by climate impacts, and a decrease in solar use in India. Now, to finish, from this research, we concluded that the two integrated assessment models provide a similar signal response to climate change impacts for most regions and energy sources. However, some differences, especially for solar energy use under both scenarios. And also, these differences are mainly related to, as I explained, power investment decisions and technological and economical assumptions. We have large positive impacts on bioenergy use under both scenarios due to the CO2 fertilization effect on yields, which is stronger, which is stronger for the SSP2 baseline scenario. On a global scale, climate change impacts induces an increase in primary renewable energy, with a slightly smaller impact for the mitigation one, and larger uncertainties were observed for the mitigation scenario based on outcome variations between the models based on the signal, and future research would benefit from including more energy models, especially for mitigation scenarios, and of course from conducting sensitivity runs on solar and hydropower too. And that's it. Thanks.
Thank you. Thank you very much, Victhalia. And any questions from the floor? From me, actually, it's just a comment, but yes, in the final slide, you said that inviting more integrated assessment models or energy economic model will be quite interesting. And I really agree with it. And if the type of the IAM different, then the behavior of the simulation may be quite different. So in order to obtain the robust results, or in order to understand how useful this type of research is, I really, yes, agree with your opinion. Thank you. And now in the chat box, we have a comment from Brian, and that's, do you plan to look at whether differences between models are coming from different impacts on potentials or from model responses to those impacts? Okay, can you answer?
Yes, I looked into in detail the reasons of the differences, and most of the differences are in relation to implementing different assumptions. For example, IMAGE implements a learning rate of technologies, so that changes over time, and also implements a interregional learning rate that, for example, if in Europe bioenergy is developed quickly, then other regions start to, and the cost reduces in this region, or better Brazil, then other regions start to implement bioenergy with reduced cost. There's an influence on the cost from one region to the other because of globalization. And yeah, I looked where there's some small causes based on the cost supply curves in tiny parts of the cost supply curves, even when there can be an expected increase in energy potential. Some tiny parts expect a decrease, an increase also in price, and then here sometimes there is a trade-off in between these two input data, and then this can cause some of the difference in between IMAGE and GCAM, and probably also with other models. But I think the main we're looking at most of the difference are mainly related to different assumptions.
Okay, thank you. And we have one more question. Maybe it will be the last, but it's from Anthony. And did you take into account agriculture and biodiversity and ecosystem degradation induced by climate change? That is the question.
No, it was mainly accounted the increase in food under the SSP2 baseline scenario because of population growth. So for calculating the possible bioenergy production, it is assumed that everybody is fed, all the world is fed, and then all this land needed for agriculture is excluded from the analysis.
Okay, thank you very much for the answer and response. And thank you very much. Now time is up, so I'd like to invite the next speaker. Thank you, Victhalia. And the fifth speaker of this session is David GARCÍA-LEÓN from JRC. And can you share the screen? And as noted in the chat box, yes, noted by Stephanie, yes, we will have 15 minutes for discussion at the end of not this impact session 1, but in the next one, impact session 2. Okay, thank you very much, Stephanie, for noting it. So now, yes, floor is yours, David.
Okay, hello. Good morning, everyone. Thank you for being here. I'm David GARCÍA-LEÓN. I'm a research officer at the Joint Research Center of the European Commission, and I'm presenting you today the progress on our reduced form damage functions for estimating the economic impacts of climate change in Europe. This is a still work in progress, and it's part of a larger project in which many colleagues from the GRC are involved. This is a very brief sketch of my presentation today. I will provide you with some, the reasons that spurred us on performing this analysis. Then we will, I will describe you very briefly the statistical analysis, the econometric analysis we have performed, by skipping most of the technical details to jump straight away into our first preliminary results and some applications of these results. Finally, I will conclude with the way ahead, the plans we have for the future. Okay, so the starting point of this analysis is the series of GRC-PESETA report. The GRC-PESETA is an analysis aimed at producing, estimating the impacts that the EU will undergo in the face of climate change in the future. This large-scale project is a multi-disciplinary project encompassing different units, different directorates within the GRC. Is based on bottom-up methodology that I will describe in the next slide, and requires, as I mentioned, large coordination between units and teams. The GRC-PESETA, by the way, it's now at its 4th iteration. So we have just delivered the 4th revision of this report. So this is in a nutshell the description of how this bottom-up approach to climate change impact works. We start on a first stage providing an outlook, a precise outlook of the climate and socioeconomic characteristics, which are fed in a second stage into some biophysical models. These biophysical models are sector-specific models, likely with very high spatial resolution, that provide us with biophysical impacts. These biophysical impacts are then included in some economic tools in order to provide some economic meaningful metrics, such as GDP impacts, welfare, and so on. As you can see, this complex bottom-up approach has, it has some pros and cons. On the positive side, we have this, it's a level of accuracy, of precision, okay? We can come up with very precise estimates of sector-specific estimates of climate change. On the negative side, it is, it is very expensive, very time-consuming, and it requires very large coordination. So it's somehow very rigid. So this is the point where emulators comes into play. Emulators are no more than statistical objects that relate our dependent variable. So in this case, climate change impacts with climate drivers. Okay, these emulators are typically statistical relationships, very simple, likely linear. They reduce the complexity of the bottom-up approach, are more tractable objects, and give us some more flexibility, more margin for maneuver. So in case we want to reassess some aspect or run new experiments, we don't need to rerun the underlying biophysical models that are behind these more complex data assessment. So emulators are becoming increasingly more popular in the latest years. On the right-hand side, you can see some examples of emulators from two research groups in the US and in Japan, based in the US and in Japan. So for our analysis at hand, we will be dealing with the PESATA report. This report comprises 10 different sectors. 10 sectors are analyzed. The simulation for the biophysical impacts are run under 11 different climate models forced by 2 different emission scenarios. Okay, impacts are typically provided at the country level annual time basis. Climate data, on the other hand, is provided on a resolution of 0.11 degrees daily time step. As you can see, there's some mismatch in resolution, so some kind of spatiotemporal aggregation is required. In our approach, we consider 4 different aggregation schemes. Okay, they are labeled with capital letters, right? So we tested what we call raw data, so country level data, annual time step. We then temporally aggregate data, the decadal time step. We perform also a spatial aggregation, providing data at the climate region level, and then D, which is a combination of a spatio-temporal aggregation. So these 4 aggregation schemes is something that we test, and then we propose 7 different statistical specification, order in complexity, in increasing complexity. Here I'm depicting you, I'm providing you with a specification number 7, which is the most sophisticated, so to say, including nonlinear effects of climate drivers and lag effects and fixed timing bar and fixed effects. So we consider for each of the 10 sector analyzed 4 different aggregation scheme, 7 different statistical specifications, and we perform a sort of horse race between models, and we select the preferred option. Now I jump straight into the main table of results. Let me guide you through this table. In each row, you will find all the 10 different sectors analyzed. Okay, and I would like to draw your attention on this column, climate variable. So, because the climate driving factors are different depending on the sectors. This is, of course, not a trivial or a random choice. This is something that we have agreed on with the experts in charge of the underlying biophysical models behind these calculations. For instance, coastal flood impacts, we, on top of temperature, we also include, of course, sea level rise. For agriculture, we select as explanatory variable heating degree days, maximum temperature for transport infrastructure, so on and so forth. Okay, the level of the goodness of fit that we obtain is somehow very decent. We obtain relatively high explanatory power. We are very happy with this, the feed that we obtain for each of the sectors considered. And now I'm going to present you with the applications. Once we have this apparatus of equations for each sector, I'm going to provide you with some applications we can run building on these emulators. And I will be focusing specifically on the case of droughts, okay? Droughts, which are explained in our case by temperature and precipitation. So I jump straight into the first application. This is something we can produce with these emulators. We can produce very easily what will be the impacts on the vertical axis. We have GDP impacts at the country level, and we can provide impacts on four different global warming levels. In this case, 1.5, 2, 3, 4 degrees, or whatever global warming level you may think of. Okay, because this is, I mean, this is the sort of flexibility that we have. Not only that, apart from having a picture, an overview of what will be the impacts on specific temperature scenarios, we can give insights on how impacts change when we jump from one scenario to the other. So what we call marginal changes in global warming levels. Here in this column, again, focusing on drought impacts, you can see how impacts will change when passing from 1 to 1.5 degrees, for instance. If you look at the plus 4.5 degrees column, or in the middle, you can find marginal changes when passing from one scenario to another scenario with 1 additional degrees. Third application, some of the potential things we can do with this tool, as Francesco has pointed out in his presentation, one of the biggest sources of uncertainty is internal climate variability. Given the fact that our estimates are built on 11 different climate models.
10 minutes, David.
Okay, I will conclude in 2 seconds. We can analyze how climate model, the range of outcomes depending on climate model uncertainty. So this is a picture, a diagram depicting a time series of impacts regarding 2 different scenarios, and considering the range of outcomes spanning from the climate model considers. And last application, I will skip the conclusion slide. Last application, this is a kind of sensitivity analysis of parameters, the parameters associated to climate variables. In this case, I'm performing a leave one out sort of exercise in which I take out one of the climate model, re-estimate the emulator, and look in particular at the coefficient associated to temperature and precipitation. And then in this fashion, we can analyze sort of the sensitivity of impacts to climate drivers. I had an additional slide pointing out the next step. I will skip for the sake of the time, and thank you for your attention.
Thank you very much for the presentation. And we have already had the first question in the comment in the chat box. And David, can you read it?
Yes. Is this table, slide 7, referring to specification 7, most complex, is the preferred model, and this based on the adjusted? Yes, okay. Yes, let me go back to that slide. I was presenting this as the most sophisticated candidate. This is actually not the preferred option for most of the sectors. Typically, lacks of temperature, lacks of climate variables are not well, are not quite significant in our specification. We typically stick to specification 5, which is basically not including lacks and not including square terms. Okay. And yes, the metric we choose to, for choosing the preferred option is typically the adjusted R-square.
Okay, thank you. Yeah, any other? Okay, we have the second question. Can you also comment on whether you'd expect to see a change in GDP growth as well as value in your model?
Can you also comment on whether you expect to see a change in GDP growth? Okay, the way we approach this exercise so far is a sort of an aesthetic nature. So we are depicting, or we are providing estimates on current euros. So we are discounting all the impacts to the present time. So and we perform differences with respect to the benchmark scenario, with respect to the present time. So so far we are not accounting for growth effects. Well, in parallel to this, as I mentioned, this is part of a larger project. A colleague of mine is running potential growth effects on GDP in the future for different climate and emission scenarios. This approach, unfortunately, is not capturing that.
Okay, thank you. And we have one more question and we have one more minute. So the third one is, can you connect the developed emulators with simple climate models?
Indeed, this is one of the extension I skipped to mention. We are planning to what we call running a probabilistic assessment of future climate scenarios, provided we have the structure of our equations based on climate drivers, on temperature, precipitation in the case of droughts. We can plug in wherever climate simulation based on whatever climate framework, climate model framework that you may think of, and run different, probabilistic assessment, as we call it.
Okay, thank you for the answer. Maybe now it's a time to move to the final presentation in this session. So thank you, David. And this final speaker is Joseph Al-Mullah from Royal Institute of Technology, KTH.
Okay, great. So hello, everyone, and thanks for this opportunity. It's a pleasure to be with you and to share some insights from the hydropower and floods analysis and some of the insights related to or from the water energy model that was developed for this analysis. On behalf of the team, I would like to share these insights. And to start with, I would like to give a quick overview about the Drin Basin, which is a shared international basin in Southeast Europe, shared between Montenegro, Albania, Kosovo, and some parts also extends to the Greekland, or in Greece. It extends over 185 kilometers and covers about 14,000 kilometer squares of area, and it's home for over 1.6 million people. In the recent years, among other challenges, the frequency and the intensity of the floods has increased, which is causing large damages. At the same time, hydropower is one of the main ingredients of the electricity mix in the region. The Drin Basin in particular contributes by about 2015 megawatts of hydropower, which is about 50% of the total hydro capacity in the region. I mean the four countries, or about 30% or 31% of the total installed capacity, if we include also thermal power plants. There are two cascades. The first one, which is in the North Macedonian part, so this is where the Drin River starts, as this is called the Black Drin, and there is the first cascade, and then it meets with the White Drin coming from Kosovo to generate the Drin River, and there is the second cascade in this part. So under the Memorandum of Understanding between the Drin riparians that was signed in 2011, a water energy food nexus study was conducted under the supervision of the United Nations Economic Commission of Europe, UNECE, and the Global Water Partnership, GWP, and of course with collaboration with the local stakeholders and ministries. Under this nexus assessment, we developed a water energy model, and the aim of this water energy model is to quantify the costs and the benefits of what you call the flood smart, or a cooperative hydropower operation regime along and between the two hydropower cascades in the Drin Basin. So our aim is to look into what will happen if we change the operational rules of the hydropower plants, what will happen to the electricity generation, how much electricity we will lose or we will gain, and on the other hand, how much or how would the flood control benefit from these changes. So these are the two main elements that we focused our analysis on. To be able to do so, we integrated two modeling frameworks. The first is a hydrological model called Pantari, and this is a hydrological model that was developed specifically for the Drin Basin, and it's used by the National Hydrology Center. And the second model is an energy model. It's called Osmosis, which stands for the Open Source Energy Modeling System. So we integrated those two models and generated a number of scenarios. And these are the main categories or groups of the scenarios: a reference scenario, climate change scenario. We looked also into the impact of a new dam, which is called the Skavisa Dam. How would this affect the generation and the flooded area, and the flood protection scenario. And due to the limited time that I have today, I would like to focus on the last scenario, the flood protection scenario. So what is the key question, or what is the idea here? So what we're trying to do is to look, okay, are we going to achieve a better flood control if we increase the buffer volume in the reservoirs? And what is the trade-off in terms of electricity generation? And by the buffer volume, I mean the empty volume that is kept empty for the flood control. So the operators are not allowed to fill up above this level. So we looked into two reservoirs, and these are one in each country: Shfilia or Spilia in North Macedonia, and Fierza in Albania. And those two has the relatively larger storage capacity, and their impact in terms of flood management is higher if we compare it to the other three. So we focused on those two, and we ran a number of scenarios looking into 5% increase, 10, 15, and 20% increase in the buffer volume. And again, increase in the empty level that is allowed for the flood control. The changes were implemented in the wet season, the months from October to May. So, and in this presentation, I'll focus mainly on the 5% and the 20% increase. So if we look at the changes, what does the 5% or a 20% mean for each reservoir? This graph shows the changes for Shfilia. So this is the additional volume. It's not the total volume, it's the additional that we gain if we change the operational rule. So we see that in Shfilia, we are gaining, the additional gains are from 7 million cubic meters or up to 34. And in Fierza, which is larger, the 5% can range from something like 36 million cubic meters all the way to 270 million cubic meters. So these are the changes in different months in the buffer volume. Okay, now the question will be, okay, we are changing, or we are increasing the buffer volume, so there will be an impact on the electricity generation. So how much is this impact? So with the energy model, we were able to look into the electricity generation from these power plants, but also from the others in the basin and the Drin Basin. And the model also included all the other electricity generation infrastructure, like the thermal power plants and hydro beyond. But here I will focus on the ones from the Drin Basin. So the changes in terms of electricity generation were very small or minor impact, I would say. In the case of Shfilia, there is a mean annual drop of 5 to 8 gigawatt hours per year. And in Fierza, it's about 5 to 34 gigawatt hours per year, and in the range of 1 to 3%. And this graph shows the change in electricity generation in Fierza and Shfilia in the years 2030, 2040, and 2050. And if we look at the changes from all the hydropower plants in the Drin Basin, which includes others, the other 5, not only from Fierza, we see that the changes are negligible, which I would say this is kind of a good sign. because the electricity sector and the utilities will not worry about this. The changes will be minor. Let us look at the impact in terms of floods and how much we are saving in flood damages. To be able to do this, we took the outputs from the water and energy model, and we used them in other two models that looked into a specific model for flood damages and a hydrodynamic model. And in this graph, we see a comparison between the reference scenario, where the historical levels of the buffer volume are kept, versus a 20% additional buffer. And we see the change in the depth or the water depth in this region, where it is an area in between Montenegro and Albania, and it's more prone to floods. And if we look at the monetary values, how much the savings would be, the first graph shows the flood damage impact in Montenegro and Albania, the downstream countries. This is the reference case, and this is the 20% additional buffer. And we see that we save about 30% in terms of flood damages in Montenegro, and all up to 60% almost in the Albanian part. To conclude, here are some final remarks. I would say, as we saw here, that changing the operational rules of the dams to accommodate floods had a minor impact in terms of electricity generation and the security of electricity supply. At the same time, this added a considerable additional volume that would be used for flood control. And as we saw also, the savings in terms of flood damages are considerable, and it's worth to explore this in more details. And this brings us to the conclusion that the energy sector has an important role to play and to contribute to flood mitigation in different ways, not only by promoting renewables, but also how we operate our renewable infrastructure can make a difference. Thank you for listening, and I will stop here if you have any questions.
Yeah, thank you, Joseph. Any questions from the floor? Since I have not found any question so far, may I ask one question, Joseph?
Please.
Yes. So in conducting this study, did you collaborate with the person stakeholder in agency for, say, social infrastructure? I mean, the audience of the study.
Yeah, so as I mentioned, this was under the Memorandum of Understanding. So we had a close collaboration with the ministries from all the riparian countries, and the outputs of this analysis would feed into something called the strategic action plan of the countries. And we had kind of a continuous dialogue with the stakeholders from the water sector, the energy sector, the agriculture, to add these results were also presented and cross-checked with the local authorities as well.
Okay, thank you very much for the answer. And any other comments or questions from the floor? You can type it in the chat box or just raise your hand. Yeah, one question from Natalia in the chat box, and it.
Yeah. So, is the hydropower model used open source? Yes, okay, no worries. Yeah, so the model that we use for the energy sector, which is osmosis, is an open source, and it models the hydropower, the thermal power plants, and other renewables as well. But here, as I said in the presentation, I just focus on the hydropower because of the relevance to the topic that we are discussing today. But yeah, it's an open source tool.
Okay, and any other questions from the floor? Okay, if there is no further questions or comments from the floor, thank you very much, Joseph, for the good presentation. Yes, so now I would like to conclude this session and thank all the speakers and participants for the cooperation, actually the contributing to this session. So thank you very much again for your cooperation. Thank you.